Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is multinomial coefficients. So let's get started. So let me remind you, we have talked about multinomial coefficients in previous videos, but you don't need to really know about those. I'm going to tell you most of what you need right here. So a multinomial coefficient, you start with a bunch of integers. In this case, I'm saying k non-negative integers, and you add them up and you get a number n. And then you define this thing n, choose n1, n2 through nk to be n factorial. N factorial was the sum of those k integers you picked, and then in the denominator you put n1 factorial, n2 factorial, all the way till nk factorial. This is a number, whatever it is. That's called a multinomial coefficient. And what we want to do is we want to study its properties and its uses and so forth. So the case k equals 2, when you have two numbers and you add them, is a special case. And that gives us binomial coefficients, the numbers that appear in the Carré-Giglia triangle, the triangle universally known as Pascal's triangle. So why is that? Well, because if you have n choose n1, n2, well, by our definition, that's n factorial divided by n1 factorial times n2 factorial. But remember, n1 plus n2 is n, so n2 is really n minus n1. And so you can write that as n factorial divided by n1 factorial over n minus 1, n1 factorial, and that's the same as n choose n1, or n choose n minus n1, which is the same as n choose n2. So n choose n1, which is a number that any combinatorics students has seen quite often, is the case k equals 2 of the multinomial coefficients. So multinomial coefficients are a more general object and one that we would like to know more about. So first of all, where does it come up? And this was the subject of a previous video, but I will quickly go over it. We will come up with multinomial coefficients when we are doing permutations of multisets. So a multiset is a set, except each element has a repetition number. It has a multiplicity. It can appear more than once. So we have this set R, and in it we have T types of elements, V1, V2 through Vt, but we have N1 V1s, N2 V2s, N3 V3s, and all the way till Nt Vts. And n is the sum of them, so n is the total number of things we have. But again, n1 of them are just identical to each other. We can't tell them apart. They're V1s, and n2 of them are V2s, and we can't tell those apart, but we can tell them apart from V1s. And we want to know what the number of n permutations of R is. So an n permutation means just a permutation. You take all of these elements of R, and you want to put them in some order, some ordered list. How many different ways you can do that? Now, if you take two n1s, two V1s, that are identical and switch them, you don't get a new permutation because those were identical. But if you switch the place of a V1 and a V2, you do get a new permutation. So the argument for this is straightforward. So I'm going to go right through it, even though it was a subject of a previous video. If I want n permutation, that means I have n spots, and I'm going to put these guys in it. Well, first I'm going to decide where the V1s are going to go. Maybe they're going to go in this spots or those spots. How many ways can I figure out where the V1s go? Well, there's n choices, n spots that I could choose from, and from those I need to pick n sub 1 places, because I'm going to place all the V1s, and the number of ways I can do that is n choose n1. That's what the definition of n choose n1 is the binomial coefficient n choose n1. Then I go and try to decide what to do with V2s. Now for V2s, I have n minus n1 spots left, because I've already used n1 of those spots for V1, so n minus 1 and 1 spots left, and I need to choose n2 of them. And then for V3s, I have n minus n1 minus n2, choose n3, and so forth till the last one. Now, if you write the formula for these things, for the binomial coefficients of the formula, again, subject of previous videos, you will get, well, that's n factorial over n1 factorial over n minus n1 factorial, n minus n1 factorial over n2 factorial, n minus n1 minus n2 factorial, and so forth. And the nice thing is that lots of these things cancel. Those n minus n1s cancel. Then n minus n1 minus n2s cancel, and so forth. And you're left with n factorial over n1 factorial, n2 factorial, and t factorial. And so the number of n permutations of a multiset with t types of elements and with multiplicities n1 through nt is n choose n1, n2 through nt. So this is where these things come from. Again, subject of a previous video. If you're not familiar with binomial coefficients, then probably this is not the right video to watch. You should be watching ones about binomial coefficients. You can also think about these, as we often do, think about this as a balls and boxes problem. So let's say you have n different balls, maybe each one of them has a number on it, and t distinct boxes to t different boxes. And what you want to do is you want to put n1 balls in the first box and 2 balls in the second box, and then t balls in box t, and n is the sum of those. So you're going to put all your balls in the boxes, but you have prescribed how many goes in box 1, how many goes in box 2, how many goes in box t. And again, the balls are different from each other and the boxes are different from each other. In how many ways can you do that? Now, the balls, you can think of them as 1 through n, and putting a ball in a box, it chooses that box. So you're putting the ball in that box. You think of that as choosing the box, and you assign a position to it, because if you put ball number 47 in that box, you're saying I'm choosing that box and I'm putting it in spot 47. So that means that each time you place all the balls in the boxes, you are giving me a permutation of the boxes. There's t types of boxes, we said, we have chosen we have put n1 balls in the box 1, and 2 balls in the box 2, and t balls in the box t, and each one of those balls had a number on it, and therefore we are saying where that box is going in the permutation. So you can think of that as a permutation of that placing of balls and boxes as a permutation of this multiset, and therefore the number of ways of placing all the balls in the boxes with these conditions is a multinomial coefficient. So that's again a place the multinomial coefficients come up. Now we're going to go back to binomial coefficients for a second, just remind ourselves what we know about them, which I'm assuming you actually know these. If you don't, do go back and learn about them. And then we want to find the corresponding things for multinomial coefficients. So when case k equals 2, when we have n choose n1, n2, or n choose k, n minus k, because the sum of that n1 and n2 has to be n, so one of them is k, one of them is n minus k, that's the same as n choose k. This is the definition of it, was the number of k subsets of a set with n elements. So how many subsets of size k does a set with n elements have? If you have n people in a room, in how many ways can you make a committee of size k? That's what n choose k is. But we also just now saw, because it's a binomial coefficient, is a special case of a multinomial coefficient, it's also the number of permutations of a multiset with 2 types of things. Often, like, for example, I can say k stars and n minus k bars. And how many permutations these have is the same as n choose k. Now, what do we know about them? One of the things we know about them is their formula. For n choose k, we know that it's n factorial over k factorial times n minus k factorial. We proved that for binomial coefficients because the definition we gave for binomial coefficients was that is the number of k subsets of a set with n elements. So therefore, we needed to prove the formula for it. For multinomial coefficients, we actually worked the other way around. We started by defining them using a formula, and then we said that, well, okay, they're count permutations of a multiset. So for multinomial coefficient, I don't need to prove a formula because that's actually where I started. But for binomial coefficients, one important thing was their recurrence relation. N choose k is n minus 1 choose k plus n minus 1 choose k minus 1, when we had a combinatorial proof of that. And you can also prove it using the formula, but that's sort of not nice. And this is the relationship that allows us to form the Carré-GGR triangle, also known as Pascal's triangle. And it says that every entry is the sum of the 2 above it. So that's an important thing, and we want to find the corresponding thing for multinomial coefficients. And one very powerful theorem that helps us with binomial identities, again subject of previous video, is the binomial theorem that says x plus y to the n is you get a typical term is x to the n minus k, y to the k, but the coefficient of that is n choose k. These are sort of the 3 important facts. These 3 important facts, and those the stuff on this page is sort of the essentials of what you need to know about binomial coefficients. And they were subject of several videos before when we went into detail. So now let's find out the corresponding things here. So let's start with recurrence relations. For binomials, we had n choose k equals n minus 1 choose k plus n minus 1 choose k minus 1. Let's write that not as binomial coefficients, but as multinomial coefficients. That same thing. Well, how would I write it? Well, n choose k is the same as n choose k n minus k. And n minus 1 choose k is the same as n minus 1 choose k n minus k minus 1. And n minus 1 choose k minus 1 is n minus 1 choose k minus 1 n minus k. And so if you look at this, we see that, well, we started here. What we did is that we subtracted 1 from the top number, both in the stuff we got, and then we needed the bottom two to add up to that, so we needed to subtract one from those, and we took turns subtracting one from one of them, one from the other one. In some sense, this is sort of looks a lot more symmetric and natural. And so what we want to do is that now for multinomial coefficients, we want to prove something similar. So now we have t integers, not just two, but t of them, and the sum of them is n. And then what I want to show is that n multi-choose, not multi-choose, the multinomial coefficient n choose n1, n2 through nt is a sum of things. It's not just two things. It goes on. It's the sum of t terms. In each term, it's n minus 1 choose something. But because it's n minus 1 choose something, and those numbers at the bottom that we're choosing should add up to n minus 1, we have to bring them down by 1, and we take turns. Once we bring down the first one, then the second one, all the way to the last one. And this is going to be the recurrence relations for them. But why is that true? And we give a combinatorial proof like we always like to do for these kinds of recurrence relations. So we say that what does a multinomial coefficient count? It counts the number of n permutations of a multiset with repetition numbers n1 through nt. And so n is the sum of n1 through nt, and the number of the n permutations so far is n choose n1, n2 through nt. Now, what I want to do is count this in a different way and say, well, okay, if I count it in a different way, then that count must match this one as long as I've not made a mistake, and the two counts must be the same. And this is the way I'm going to say. I'm going to say, well, here, if you want to find a permutation of these n things, well, you've got to start with something. What are you going to start? Well, if you start with u1, with that first thing, if you don't permit, you don't have to have u1 first. But what if you did start with u1? Well, if you do that, then you put u1 down. Now you have to find what the other n minus 1 things are going to be. And what you need is a permutation of n minus 1 things. What n minus 1 things? Well, the set that has n1 minus 1 u1s, and 2 u2s, and t uts, because you just used one u1. Now you have one less u1 to place in that permutation. And therefore, the number of ways of doing that by what we have just talked, we've talked about multinomial coefficients, it's as n minus 1 choose n1 minus 1, n2 through nt. But that's not all the n permutations so far, because they don't all start with u1. This is the ones that do start with u1. If they start with u2, then what it is, same argument. You put a u2 down, now you have one less u2, and you have to find a permutation of all the other n minus 1 things. And the answer is going to be n minus 1 choose n1, n2 minus 1, all the way till n2. And you keep repeating that. And then the last one is going to be n minus 1 choose n1, n2 through nt minus 1. And that counts the number of n permutations so far that start with ut. And so because every permutation starts with one of these guys, then the sum of these should be the same as the original answer we had, which was just one multinomial coefficient. So if I add all of these, I should get that. So that's the proof. And so what did we prove? We proved that if you have a bunch of non-negative integers and n is their sum, then we have this recurrence relation for the multinomial coefficient. Okay, so now let's try to generalize the binomial theorem. The binomial theorem was that if n is a non-negative integer, then for all x and y, x plus y to the n is a sum of these terms. Each term, the actual term is x to the n minus k, y to the k, but the coefficient of that is n choose k. Now, what we want to prove is the multinomial theorem, which is a generalization of the binomial theorem. And it says that if n is a positive integer and you have x1 plus x2 plus xt raised to the power n, you also get a sum. And the typical term is x1 to the n1, x2 to the n2, xt to the nt. But the coefficient of that is n choose n1, n2, nt, a multinomial coefficient. Now, note that I didn't say what the summation starts and where it ends. And I'm not going to quite say it starts here, it starts there, because actually I've got to change a lot of different things. I have a term for this. I have a lot of terms in this sum. And in fact, I have a term for any solution to n1 plus n2 plus nt equals n. So what does that mean? That means that you're given n. So when you want to expand x1 plus x2 plus xt raised to the power n, you're given n, but you're not given n1 plus n1, n2, nt. You say, okay, what is some possible ways of finding t integers that add up to n? For every one of those ways that you can do that, for every way that you can find an n1, n2, and nt all the way to nt that add up to n, you get one term. So as soon as you find a solution, you put those n1 through nt's as the exponents of x1 through xt, and you put a multinomial coefficient in front of them. You do all of those and add them, and you get and I get x1 plus x2 plus xt to the n. No one said that there's going to be few terms. There's going to be a lot of terms. In fact, how many terms are there is going to be the number of non-negative integer solutions to x1 plus x2 plus xt equals n. That was the subject of previous videos, is a multi-choose number. It's t plus n minus 1, choose t. Choose n. Okay, so let me give you an example of how to use this theorem, and then we'll give a proof of it. So let's say that we have x plus x inverse plus 2x to the minus 4 raised to the power 17, and I want to find the constant term. By the multinomial theorem, a typical term in the expansion is something like this. Because it's raised to the 17th power, that typical term is 17ijk, x to the I, x inverse to the j, 2x to the negative 4 to the k, because though the terms are not x, y, and z, they're x, x inverse, and 2x to the minus 4, this is going to be our typical term. And so, and what are ij and k? There's anything between 0 and 17, and they have to add up to 17. So they're all non-zero, and they have to add up to 17, so none of them can be more than 17. But more than that, we don't want all the terms. We want only the constant terms. How am I going to get a constant? I'm going to get a constant if all the x's cancel. That means if I minus j minus 4k, because x to the minus 4 to the k is my x to the minus 4k, is 0. So I also want I minus j minus 4k be 0. So you have to find what are all the solutions to these two equations with those restrictions. And there are various ways of doing that. For example, you can subtract them. And if you subtract them, the i's go away. And then you can see that k can only be 1 and 3. You can think about even and oddness for a second. And there's a limit on how big k can be. And you can find the common integer solutions and find that there's only 2. Either k is 1 or k is 3. And based on those, you know what I and j are. So one solution is when I is 10, j is 6, and k is 1. Another one is when I is 13, j is 1, and k is 3. And each one of those gives us one term that will be a constant term, because this part will become, the x part of it will become 0. And now for each one of these, we will have a coefficient. So what's the coefficient of the first one? Is, well, 17, 10, 6, 1. The 10, 6, 1 came from I, j, and k. But remember, when k is 1, this term here, it has a 2. So that also gets multiplied. So I have 2 times that. When k is 3, that 2 becomes 2 cubed. So I have to remember to multiply by 2 cubed. But the multinomial coefficient is 17, 13, 1, 3, which is what I, j, and k are. And if you find that, if I haven't done a mistake, most likely I have, is 348,432. Okay, now, final thing. Why is this about multinomial theorem true? So I want to expand this guy. Well, the typical term is going to be something like x1 to some power, x2 to some power, xt to some power, because we're taking n parentheses, each with x1 plus x2 plus xt, x copies of x1 plus x2 all the way till xt, and then multiply them. Every term is going to be of this form, x1 to the n1, x2 to the n2, all the way to xt to the nt. And the sum of those exponents got to be n, because we have got to pick n of them. And each ni is a non-negative integer. So each typical term is that. The question is that how many times do I get each one of them? Because how many times I get each one of them is going to be what its coefficient is. So we're expanding x1 plus x2 plus xt multiplied by itself n times. And I want to know how many times I get x1 to the n1, x2 to the n2, all the way till xt to the nt. But how do I multiply these? Well, when you multiply n parentheses like that, you have to pick something from the first parentheses, something from the second parentheses, something from the third, something from the last, and multiply them. And as soon as you decide that, okay, this is the guy that comes from the first one, this is the guy that comes from the second one, and so on, you have a permutation of, you have something like x2 came from the first parentheses, x5 came from the second parentheses, x2 again came from the third parentheses, and so forth. And that's a permutation of what? Is a multiset. n1x1s and 2x2s and ntxt's. Why n1x1s? Because I'm trying to see how I'm going to get x1 to the n1, x2 to the n2. So I need to pick n1x1s and 2x2s and ntxt's. So I need to permute these guys. And as soon as I have a permutation of them, I've told you how to pick from which parentheses, which one of these xi's to get an x1 to the n1, x2 to the n2, and xt to the nt. So there's a one-to-one correspondence. Every time I get that term, I've got myself a permutation of this multiset, and every time you give me a permutation of this multiset, I get a recipe for how to find a term of this form. So the number of ways that I get x1 to the n1 through x to the nt is the same as the number of permutations of this multiset, and we already have seen that that's a multinomial coefficient, and so that works, and so that is the coefficient, and so x1 plus x2 to xt to the n is the sum. But again, where did the n1 through nt comes? There are all possible solutions to n1 plus n2 plus nt equals n. So you start with n, you don't have n1 through nt, and then you say, okay, well, n is 5, but how am I going to get 5 from 3 things? Well, maybe 1 plus 2 plus 2. So n1 could be 1, so that gives you one term. Oh, but maybe it could be 2, 1, 2. So that gives you another term. Or maybe it could be 4, 1, 0. That gives you another term. Every solution to n1 plus n2 plus n3 equals 5 then gives you a term for this. This is the end of this lecture. If you like to be subjected to more videos like this, please like and subscribe. If not. And I will see you in a future lecture.